What if I told you there's an engine so powerful that two different racing organizations banned it within 12 months of its debut? An engine that made 100 more horsepower than anything else on the track, not through exotic materials or space-age technology, but through one mechanic's obsession with hemispherical combustion chambers and valve angles that everyone else said were impossible to manufacture. Picture this. It's February 23rd, 1964. Daytona 500. Richard Petty crosses the finish line at 174th Ford 18 miles per hour, 9 miles per hour faster than the previous year's winner. Behind him, Jimmy Pardue. Behind him, Paul Goldsmith. Plymouth, Dodge. First, second, third. The crowd doesn't know what they're witnessing yet. They're watching the debut of an engine that would become so dominant, so utterly superior to everything else on the track, that NASCAR would literally rewrite their rulebook to stop it. The 426 Hemi had arrived, and motorsports would never be the same. This is the story of how Tom Hoover, a Detroit mechanic who started his career grinding valves at Chrysler's engine lab, created a power plant that redefined what stock racing meant. How his hemispherical combustion chamber design extracted performance that shouldn't have been possible from pump gas and production line parts, and how that engine became so feared that competitors lobbied racing organizations to ban it outright, calling it an unfair advantage that threatened the very nature of stock car racing. To understand why the 426 Hemi sent shockwaves through motorsports, we need to travel back to 1963. NASCAR was exploding in popularity. Ford and General Motors were locked in a bitter horsepower war, each spending millions to dominate Sunday races and boost Monday sales. Win on Sunday, sell on Monday wasn't just a catchy phrase, it was corporate doctrine. Ford had their 427 FE making 425 horsepower. Chevrolet countered with the mystery motor, their 427 Mark II pushing similar numbers. Both companies had deep pockets and decades of racing development. Chrysler? They were the underdog. Their biggest engine was a 426 cubic inch wedge making 415 horsepower on its best day. Respectable, but not race-winning. Not when Ford and Chevy cars were walking away from them on every super speedway. Chrysler's racing program was hemorrhaging money. Dealers were complaining. Something had to be done. Lynn Townsend, Chrysler's president, called a meeting in the fall of 1963. The directive was simple and impossible. Beat Ford and Chevrolet at Daytona. You have 4 months. The budget? Whatever it takes. But here's the kicker. It had to be based on a production engine. NASCAR's rules were clear. Stock cars raced stock engines, or at least engines that looked stock to scrutineers. Enter Tom Hoover. At 36 years old, Hoover wasn't your typical Detroit engineer. He'd started at the bottom, literally grinding valves as a technician, before working his way up to engine development. While his contemporaries focused on incremental improvements, Hoover was obsessed with combustion chamber geometry, specifically hemispherical chambers, a design Chrysler had experimented with in the 1950s before abandoning it as too expensive. The principle behind a hemispherical combustion chamber is beautifully simple. Picture a normal wedge-shaped chamber. It's basically a slice cut into the cylinder head, with valves sitting at an angle on one side. Functional, but compromised. The flame front has to travel across that wedge, and the valves can only be so big before they hit each other. Now imagine a perfect dome carved into the head. The spark plug sits at the apex. The valves oppose each other at optimal angles. The flame front propagates evenly in all directions. The valves can be massive. It's geometrically ideal for combustion. But here's where it gets interesting. Everyone knew hemispherical chambers were theoretically superior. The problem was making them work in a production engine. The valve train complexity alone was a nightmare. You needed dual rocker shafts, complicated push rods, precisely machined chambers that cost 3 times as much to manufacture as wedge heads. Racing teams had been building custom Hemi heads for years, but they were hand-fabricated, one-off pieces that cost more than most people's houses. Hoover's innovation wasn't the hemispherical chamber itself. It was figuring out how to mass-produce it. Working with a team of 12 engineers in Chrysler's Highland Park facility, he developed a casting process that could create consistent hemispherical chambers. The key was the valve angle, 58 degrees included. Any steeper, and the push rods wouldn't clear the intake ports. Any shallower, and you lost the hemispherical advantage. That specific angle, Hoover discovered, was the sweet spot between performance and manufacturability. The first prototype was ready by December 1963. On the dyno with a single 4-barrel carburetor, it made 425 horsepower. Impressive, but not earth-shattering. Then Hoover did something that would become legendary. He bolted on a cross-ram intake manifold with two 4-barrel carburetors. The engine screamed to 7,000 RPM and produced 525 horsepower. Let that sink in for a moment. Stock displacement, stock bore, and stroke. Pump gas, 525 horsepower. Ford's best race engines were making 425. Chevrolet's Mystery motor topped out at 430. Hoover's Hemi was making 100 horsepower more, not through exotic materials, not through radical displacement, through superior breathing and combustion efficiency. The specifications were pornographic for 1964. Bore and stroke, 4.25 x 3.75 inches for exactly 426 cubic inches. Compression ratio, 12.5.1, right at the limit for high-octane pump gas. The intake valves measured 2.25 inches. The exhausts, 1.94 inches. For perspective, a contemporary big-block Chevy used 2.19-inch intakes. The Hemi's valves were so large that Hoover had to offset the bores by 1875 inches just to clear the valves. The camshaft was equally radical. Duration at 0.50-inch lift, 284 degrees intake, 292 degrees exhaust. Lift, 528 inches intake, 536 inches exhaust. The overlap was aggressive enough that the engine barely idled, loping at 950 RPM like it wanted to eat something. The valve springs were dual coils rated at 420 pounds open pressure. They had to be. At 7,000 RPM, those massive valves were opening and closing 58 times per second. But raw specifications don't tell the whole story. What made the Hemi truly revolutionary was its complete system integration. The cross-ram intake wasn't just two carburetors on a manifold. Each carburetor fed the opposite bank of cylinders through runners tuned for 5,800 RPM. At that speed, the intake pulses created a supercharging effect, cramming extra air into the cylinders. The headers were equally sophisticated, equal-length tubes calculated to create scavenging effects that pulled exhaust out of the cylinders. Chrysler built 25 race engines for the 1964 Daytona 500. Each was hand-assembled at Highland Park by Hoover's team. The blocks were magnafluxed for cracks. The crankshafts were X-rayed. Every component was balanced to within half a gram. The total cost per engine, $15,000. That's $140,000 in today's money for one engine. Testing began at Chrysler's Chelsea Proving Grounds in January 1964. The results were devastating. On the 4.7-mile oval, test driver Charlie Gray lapped at 181 miles per hour. The previous record was 171. In the draft, working with another Hemi-powered car, they hit 195 miles per hour. The engineers didn't believe the timing equipment. They tested again and again. The numbers were real. But here's the thing about revolutionary technology. It rarely works perfectly the first time. During a 500-mile durability test, engine number 7 threw a rod through the block at 6,800 RPM. Analysis showed the connecting rod bolts had stretched. Hoover redesigned them with larger shanks. Engine number 12 dropped a valve at full throttle. The keeper grooves were redesigned. Engine number 18 cracked a cylinder head between the valve seats. The casting process was modified to add material in that area. Each failure taught them something. By the time they arrived at Daytona, they had 19 race-ready engines and 6 months of failure analysis. Hoover personally supervised the installation of each engine. The instructions were specific: 7,000 RPM maximum in qualifying, 6,800 in the race. Any driver who exceeded those limits would answer to him personally. February 21, 1964. Daytona 500 qualifying. Paul Goldsmith, driving the number 25 Plymouth, records a lap at 174.910 miles per hour. It's not just a pole position, it's 4 miles per hour faster than the previous year's pole. Richard Petty qualifies second at 174.418, Jimmy Pardue third at 173.930. The top 5 qualifiers, all Hemi powered. Ford and General Motors engineers stood in the pits with stopwatches, unable to believe what they were seeing. The race itself was a massacre. Petty led 184 of 200 laps. When mechanical problems took him out of contention, Jimmy Pardue took over. Plymouth and Dodge drivers occupied the top 5 positions for most of the race. The only non-Hemi car to lead a lap was Marvin Panch's Ford, and that was only because the Chrysler teams were in the pits. Junior Johnson, driving a Dodge with Hemi power, put it bluntly in a post-race interview, "It ain't fair. That motor's got so much power, you could put it in a school bus and win races." The aftermath was swift and brutal. Within 48 hours, Ford's racing director, Leo Beebe, filed a formal protest with NASCAR. General Motors joined them. Their argument was simple: the Hemi wasn't a production engine. You couldn't walk into a Chrysler dealer and buy one. It violated the spirit of stock car racing. NASCAR President Bill France was in a bind. Technically, Chrysler hadn't broken any rules. The regulation said engines had to be available to the public. They didn't specify when or in what quantity. Chrysler promised to build street versions, eventually. Maybe. But Ford and GM were threatening to pull out of NASCAR entirely if the Hemi was allowed to continue. That would kill the sport. On April 14, 1964, France made his decision. The Hemi was banned from NASCAR competition unless Chrysler made it available as a regular production option in passenger cars, not race cars, street cars, with warranties and dealer support and production numbers that proved it was genuinely available to the public. The NHRA followed suit 2 weeks later, implementing cubic inch-to-weight penalties that effectively neutered the Hemi's advantage in drag racing. The USAC banned it from Indianapolis. Within 60 days of its first victory, the 426 Hemi had been legislated out of existence in every major racing series in America. Chrysler's response was exactly what you'd expect from a company that had just spent millions developing a race engine. They built a street version, but not just any street version. They detuned it as little as physically possible while still making it streetable. The Street Hemi, introduced for the 1966 model year, was a masterpiece of malicious compliance. Compression dropped from 12.51 to 10.5.1. The radical solid lifter cam was replaced with a hydraulic unit. Cast iron exhaust manifolds replaced the headers. A single 4-barrel carburetor sat atop an aluminum intake. The advertised output was 425 horsepower at 5,000 RPM and 490 lb-ft of torque at 4,000 RPM. Those numbers were hilarious lies. Every magazine that tested a Street Hemi found it made closer to 500 horsepower. Hot Rod Magazine's test car ran the quarter mile in 13.5 seconds at 105 miles per hour, completely stock. On street tires. With a full exhaust system, a contemporary 427 Corvette weighing 700 pounds less ran 14.2 at 99 miles per hour. But here's where Hoover's genius truly shined. The Street Hemi was essentially the race engine with a mild cam and a lower compression. Every internal component was race spec. The forged steel crankshaft was good for 8,000 RPM. The connecting rods were forged steel with bolts sized for 650 horsepower. The pistons were forged aluminum with valve reliefs cut for cams that Chrysler would never officially sell, but everyone knew existed. The cylinder heads were identical castings to the race engines. Same valve sizes, same port volumes, same hemispherical chambers. The only difference was the valve springs. Single coils rated for 6,500 RPM instead of duals rated for 7,500. A $15 set of springs was all that separated a street Hemi from a race Hemi. The street Hemi option cost $877.55 in 1966. That's $7,800 today, just for an engine option. It required mandatory heavy-duty everything: transmission, rear axle, suspension, brakes, cooling system. A fully optioned Hemi Plymouth Satellite stickered at $4,100. A house in suburban Detroit cost $15,000. Chrysler built 10,119 street Hemis between 1966 and 1971. Each was hand-assembled at the Marysville, Michigan engine plant. The assembly line workers called it Hemi Row, a separate area where engines were built one at a time by specialists. Each engine took 4 hours to assemble versus 45 minutes for a standard 440. The stories from the street Hemi era are legendary. Don Garlits running 8.35 at 172 miles per hour in a top-fuel dragster with a basically stock Hemi bottom end. Sox and Martin's Pro Stock Barracuda dominating NHRA with a Hemi that made 680 horsepower using factory parts and valve train geometry that Tom Hoover had designed on a napkin. Richard Petty winning 27 races in 1967 with Hemi power, including 10 in a row. But the real vindication came from Ford and General Motors. By 1968, both companies had developed their own semi-hemispherical combustion chambers. Ford's 429 Super Cobra jet used modified wedge chambers that approached hemispherical efficiency. Chevrolet's ZL1 427 used similar technology. They called them semi-Hemi or modified wedge designs, but everyone knew what they really were: acknowledgement that Tom Hoover had been right all along. The insurance companies killed the street Hemi in 1971. Premiums for Hemi cars had reached $3,000 per year. That's more than most people's car payments. Sales dropped to 356 units. Chrysler discontinued the option, claiming emissions regulations made it impossible to certify. The real reason was simpler: nobody could afford to insure them anymore. So what was actually going wrong? Why did an engine design that was geometrically perfect become too dangerous for the street? The answer lies in the very characteristics that made it dominant on the track. The Hemi was always a race engine pretending to be a street engine. That massive valve overlap meant it barely idled. The compression ratio, even detuned, required premium fuel. The valve train. Geometry put tremendous stress on components. Street Hemis needed valve adjustments every 3,000 miles. But the real problem wasn't mechanical. It was psychological. The Hemi attracted a specific type of owner: someone willing to pay double for an engine option, someone who understood what 490 lb-ft of torque meant, someone who knew that their 425 horsepower engine was actually making 500. These weren't people buying transportation. They were buying barely legal race cars. The accident statistics were damning. Hemi cars were involved in fatal accidents at 3 times the rate of standard muscle cars. Not because the engine was inherently dangerous, but because it enabled velocities that 1960s chassis technology couldn't handle. A Hemi Roadrunner could hit 140 miles per hour. It had 4-wheel drum brakes designed for 100 miles per hour. The suspension was engineered for drag strips, not corners. The tires were bias-ply rubber with the grip of modern bicycle tires. Modern Hemi enthusiasts like to claim the engine was ahead of its time. That's not quite right. The Hemi was exactly of its time, a pure expression of 1960s American automotive philosophy. Maximum power, minimum compromise, let the driver sort out the consequences. It was engineering without boundaries, performance without limits, speed without apology. Today, An original 426 Hemi engine is worth more than most houses. Complete street Hemi cars trade for six figures. Numbers matching documented race Hemis have sold for over $250,000, just the engine, not the car, the engine alone. At the Mecum auction in January 2023, a 1964 race Hemi with documented NASCAR history sold for $385,000. But here's what's really interesting. Chrysler never stopped developing the Hemi. In secret, Tom Hoover's team continued refining the design throughout the 1970s. They developed aluminum blocks that weighed 100 pounds less. They created cylinder heads with ports that flowed 400 CFM, 35% more than the original. They designed roller camshafts that would have made 700 horsepower reliable. None of it saw production. The oil crisis, emissions regulations, and insurance industry had spoken. The era of unlimited performance was over. Hoover retired in 1979, taking with him 40 years of engine development knowledge. He died in 2013 at age 85, having lived long enough to see Chrysler resurrect the Hemi name for their modern engines. The modern Hemis share nothing with the 426 except marketing. They use twin-plug chambers that are more wedge than hemisphere. They're good engines, efficient, powerful, reliable. But they're not Tom Hoover Hemis. They're not the product of one engineer's obsession with geometric perfection and volumetric efficiency. They're not race engines masquerading as street engines. The 426 Hemi remains the most dominant engine in motorsports history. It won NASCAR championships. It owned NHRA Pro Stock. It powered top fuel dragsters to speeds people thought impossible. It did. All this with 1960s technology, no fuel injection, no computer controls, no variable valve timing, just perfect geometry and precise manufacturing. Think about that for a second. In an era before CAD software, before computational fluid dynamics, before any of the tools modern engineers take for granted, Tom Hoover designed an engine so superior that racing organizations banned it, not restricted it, not handicapped it, banned it. They literally rewrote the rules of racing to stop one engine. That's not just engineering, that's sorcery. The lesson of the 426 Hemi isn't about hemispherical combustion chambers or valve angles or intake manifold tuning. It's about what happens when you give brilliant engineers freedom to build without compromise, when winning matters more than cost, when performance is the only metric that counts. You get engines that are too good for their own good, too powerful for their era, too pure for the real world. Modern automotive engineering is about balance, efficiency, emissions, safety, cost, reliability. Everything gets weighted and optimized. The 426 Hemi was from a different time, a time when the only question was how fast. The only limit was the courage of the driver. The only goal was to win on Sunday. We'll never see anything like it again. Not because we can't build engines that powerful. Modern technology makes the Hemi's output look quaint, but because we'll never again have that perfect storm of corporate competition, regulatory freedom, and engineering ambition that created the 426 Hemi. It was a moment in time when American automotive engineering reached for the absolute limit of what was possible and grabbed it with both hands. The next time you hear a modern muscle car rev its engine, remember that its spiritual ancestor was so dominant that it had to be banned. That somewhere in a Detroit warehouse in 1963, a mechanic named Tom Hoover was grinding valve seats to impossible tolerances, chasing geometric perfection, building an engine that would become legend. And when people ask why the 426 Hemi matters, why collectors pay fortunes for rusty blocks and worn cylinder heads, tell them this. It was the last time anyone built an engine without asking, should we? They only asked, can we? The answer changed racing forever. What's the most legendary engine story you know? Drop it in the comments below. I'll catch you on the next one.